Quantum computers and classical computers are fundamentally different in how they process information. Classical computers use bits as the basic unit of data, which can be either 0 or 1. Quantum computers use qubits as the basic unit of data, which can be in a state of 0, 1, or both due to superposition. Quantum computers utilize the principles of superposition and entanglement in quantum states, setting them apart from classical computers, and have the potential to revolutionize fields requiring immense computational power. So, what is superposition and entanglement? Superposition refers to the ability of a quantum system, like an atom or a particle, to exist in multiple states at the same time. Unlike classical physics, where something is either in one state or another, quantum systems can be in a blend of states. Imagine a coin. In the classical world, it will be either heads or tails. But in the quantum world, while the coin is spinning, it's in a superposition of both heads and tails simultaneously until you observe it. Once you look, it collapses into one of the definite states. This concept is fundamental to quantum computing, where qubits can represent both 0 and 1 at the same time, allowing quantum computers to process vast amounts of data more efficiently than classical computers. Quantum entanglement is a fascinating phenomenon in quantum physics, where particles become interconnected in such a way that any changes to the state of one entangled particle immediately impacts the state of the other, no matter how far apart they are. Imagine it like this. You have two dice. Normally, the roll of one die doesn't affect the other. However, if the dice were entangled, rolling a 6 on one would mean the other die would instantly reflect this outcome, whether it's on your table or on the other side of the universe. Quantum entanglement is crucial in quantum computing because it allows for the creation of correlations between qubits that classical computers cannot achieve. For example, enhanced processing power, improved communication and security, and error correction. So, what can be used as qubits, the fundamental building blocks of quantum computing? Superconducting circuits leverage materials that exhibit superconductivity, meaning they have zero electrical resistance at very low temperatures. These materials form circuits that can represent quantum states. Trapped ions use the electronic states of ions trapped in an electromagnetic field. Individual ions are trapped and manipulated using electromagnetic fields. Topological qubits rely on the properties of topological states of matter and are considered to be more robust against errors. Photonic qubits use the polarization or path of photons to represent qubit states. Information is encoded in the quantum states of photons. This type of qubit is particularly useful for quantum communication. Spin qubits use the spin states of electrons or nuclei. These use the spin states of electrons in silicon as the basis for qubits and have the advantage of compatibility with existing semiconductor technology. Nitrogen vacancy centers in diamond. Defects in diamond crystals can be used to create qubits. These are particularly noted for their stability at room temperature. Each type of qubit has its own advantages and challenges, and researchers are continually working to improve and find the best systems for building practical quantum computers.